Hi, everyone. I would like to present you this very fresh study that appeared on Archive today. I will start with this plot on the left that you have already seen in the previous presentation. It comes from this paper by Marshall et al. 2010. I will remind you what is going on here. There is a record long optical polarization plane rotation of 720 degrees. And there is a set of flares in the gamma rays and in the optical along this rotation and just before it. Interestingly, these flares have a very different ratio of gamma ray to optical flux, and presumably some of them are produced by the external Compton mechanism and others are by synchrotrons of Compton. And the model explaining this set of events here is demonstrated on the right sketch. We have an emission feature moving through the acceleration and collimation zone, which is permitted by the helical magnetic field. Since it traces different orientations of the magnetic field on its path, we see this polarization plane rotation. At the same time, in the sheath of the jet, there are several other emission features that are presumably relatively stable and probably look more or less like ring-like structures. When the moving emission feature passes through these rings, it upscatters the photons to gamma rays, so we see the external Compton flares. And at the end of the acceleration and collimation zone, this emission feature hits the standing conical shock that we presumably see as the radio core in VLBI maps. So at this moment, we see the new radio node appearing at the end of the rotation. And also, at this moment, the magnetic field lines are very much aligned with the shock front. So we see a strong polarization at this moment and a bright synchrotrons of Compton flare. So interestingly, this model and this paper has a very clear and falsifiable prediction that is written here. So shortly saying, if these rings in the sheath are stable enough, are persistent enough, then the next emission feature propagating through the same path should exhibit the same pattern of external Compton flares. So we should be able to see again the same pattern of gamma ray flares. So I wanted to test this prediction, and I went to the literature, collected data on EVP rotations, found blazars with more than one EVP rotation, processed Fermi-Lat gamma ray data for the corresponding time intervals. And as you may guess from the title of my talk, it was successful. I found this blazar 3C279. Here in the panels A, B, C, D, you can see the photon gamma ray flux from Fermi-Lat, R-band magnitude, polarization, optical fractional polarization in this panel C, and the position angle of the electric vector or the direction of the polarization plane on the bottom plot. There are these three pink regions. They show the three largest EVP rotations in this blazar. And if we plot the gamma ray the gamma ray curve for these regions in between the vertical dashed lines marked with numbers 1, 2, and 3, we plot them here, and we see something that it doesn't look like a pattern, right? But we know that emission features propagate with different velocities in the jets because we see it directly in the VLBI. So if we adjust the time axis of the second and third event, we see the pattern. Here you see the coefficients that were used for adjusting the time scale. And you see that the three pieces of a light curve look very similar, especially the first and the third one. And I emphasize that there is 6 years between the first and the third piece of a gamma ray curve. So we believe this pattern is exactly what was predicted by Marshall et al. 2010. Now, you may see that during these 3 seasons, alpha, beta, gamma, there is no so much activity in the polarization plane as it was in the previous 3 seasons here. But if we plot these 3 seasons, these dots on the Stokes, on the relative Stokes parameters plane like it's shown here, we see that the centroids of each distribution is shifted away from the 0, 0. So this presumably happens because there is an underlying highly polarized quasi-constant source. And even if the variable source was rotating the polarization plane, we would not be able to see it in the EVPA curve because the rotation of the loop on the QU plane is not around 0, 0. So we cannot see anything happening in the EVPA in principle. Fortunately, our Japanese colleagues developed a special application that is cited here that helps you to find rotations on the QU plane, the loops on the QU plane. So I ran this data through their application and found this loop, part of a loop. If you shift all this distribution to the 0, 0 with parallel shift, this part of the loop would correspond to 120 degrees EVPA rotation, which would be here in this hatched pink region. And again, if we take the gamma ray light curve during the pretty much the same interval in between these two vertical dashed green lines, we will see this curve shown by magenta points if we stretch it by the factor of 2.5. So it again looks pretty similar to the interval 1 in the gamma ray curve. And we believe this is the fourth repetition of a gamma rays pattern that was coincident this time with a hidden EVPA rotation. Now, in the paper by Professor Marsher and co-authors in 2010, there were ejection of radio nodes in the 43 gigahertz radio maps. We have them as well. So we took the ejection times of new nodes from these two papers, and we associate our events with the following nodes. So event 3 we associate with C36 that happened right after the rotation. Event 4 is presumably associated with C34. For the event 2, we don't have any node.
3 more minutes, Dima.
We don't have any node ejected here, but as you see, there are no nodes for a 3 years interval here, and this is presumably related to these two very bright nodes, C32 and C31, that were propagating within the first mass milliarc second from the core, and they were extremely bright. They were 4 times the flux of the radio core, so no new nodes could be registered this time. And for the first event, for the first rotation and pattern, we have 2 candidates. It could be C29 node or C32, so we have not decided which one produced this event. So as you may understand from my talk, we believe that this model, this scenario proposed by Marsher et al. In 2010 is the best model describing the set of events. However, don't misunderstand us. We don't think that all EVPA rotations in blazars are produced by this mechanism. So we know that there are super fast rotations of the polarization plane that happen on the timescale of hours or days, and they are probably cannot be explained by this model, and probably they are explained by the magnetic reconnections, as you heard from the previous talk. On the other hand, we are sure that this model works for this particular blazar, and if you are not convinced, we have one more observational test for you that will be available in the near future. So it has been shown in recent works by Kovalov and his group that there are significant VLBI to Gaia offsets in positions of AGN. And moreover, these VLBI to Gaia offsets were systematically aligned with the jet's directions. And they are presumably explained by the fact that we are resolving, we are so accurately finding positions of sources in radio and in optical. So our astrometry is so accurate that we can actually resolve the substructures in the AGN. Later, I joined this group for one paper where we demonstrated in this recent paper that actually optical polarimetric properties are correlated with VLBI Gaia offsets. So sources with VLBI Gaia offsets pointed downstream the jet, they have significantly higher optical polarization compared to the opposite case. So combining together all what I mentioned before, and if these models are correct, then we expect that during the patterns and the rotations that I mentioned before, we would be able to see so-called VLBI to Gaia offset jitter. If we extrapolate motion of this node C36 to the beginning of the pattern, to this moment of this vertical dashed line, we should see the component somewhere here, shown by the red dot. At this moment, we obviously would not be able to see it in the radio because tau1 is reached in the core here. But at the same time, in the optical, the jet is transparent. So potentially, Gaia optical photocenter should be shifted upstream the core. Unfortunately, monitoring data from Gaia is not available for the moment, but it will be available in future data releases in a few years. But now we already can see manifestations of this jitter in the existing Gaia data. In EDR3, there is a proper motion for this source, significant one, and the position angle of a proper motion is pointed exactly along the jet, but in the upstream direction. Moreover, there is this quantity astrometric excess noise in the catalog, which also indicates that there are some unaccounted motions of the photocenter in the Gaia data. So we are looking forward for the future Gaia data releases, and we expect to test our models even better with those data. And I leave you with my conclusions. Thank you for your attention.